In this lecture, we will review together Chapter 6, which is about momentum, impulse, and collisions. This is one of my favorite subjects. Understanding momentum, impulse, and collisions allow us to understand motion better, allow us to understand many of the phenomena occurs around us better. Like if two objects collide, what physics governs the collision? How to analyze such a problem? If rocket is fired, what kind of force is there? What governs the motion of the rocket? If you are having a rifle and you fire, you will note that the rifle is pushing back on you. Why this happens? We will have a better understanding of mechanics. This will help us to improve how we play games, not golf only, all kinds of sport activities. You will be able to perform better once you have a good understanding of momentum and impulse. Very well. So what is momentum? We are all familiar with the word momentum in our daily use of the word. However, in physics, like energy, kinetic energy, like work that we learned in the previous chapter, in physics, momentum has specific meaning. Momentum means the product of mass by velocity. Since velocity is a vector quantity, then momentum is also a vector quantity. Momentum, thus, is a physical quantity that has both magnitude and direction, like all vectors. The unit of momentum in the SI system is a unit of mass multiplied by a unit of velocity. So it is measured in kilogram meter per second. As you can see from this defined formula, momentum is a function of mass and velocity. Kinetic energy is also a function of mass and velocity. But kinetic energy, as we defined it last chapter, it is equal to 1/2 mv squared. So both are function of mv. Therefore, we can define the kinetic energy also in terms of the momentum. So kinetic energy equals p squared over 2m. Then, since momentum is a vector quantity, like all vectors, we can decompose it into components, like we can deal with two-dimensional space, horizontal axis x, vertical axis y. Then we have a component for the momentum along x equals mvx, and another component along y equals mvy. We can always superimpose these components using Pythagorean theorem. So px squared plus py squared underneath square root is equal to p in magnitude. So just like another vector, you can decompose it into components, and also you can superimpose these components to get the whole vector value. And this is a very nice equation here. We can calculate the kinetic energy from the momentum if we know the mass. So it's p squared over 2m. Two masses, m1 and m2, with m1 less than m2, have equal kinetic energy. How do the magnitudes of their momenta compare? So now we know that kinetic energy 1 equals kinetic energy 2, and we know that m1 is less than m2. So we have all the information that we need to tell about the momentum. Since M1 is less than M2, then P1 should be less than P2. Because kinetic energies are equal, P squared over 2M for the first equals P squared over 2M for the second. So we can solve for P1 over P2 from this equation. The answer is square root of M1 over M2. Since M1 is less than M2, then P1 must be less than P2. The second quantity that we need to learn about in our study today is impulse. Impulse is related to momentum. Consider what we learned in our study of Newton's law. We learned that the net force, the net external force equals ma, mass by acceleration. And we know from the kinematics that A equals delta V divided by delta T, right? So now if you have the mass with a velocity here, this becomes delta mv. And what is mv? mv is just the momentum, right? It is the momentum. So the net force from this simple derivation is equal to delta P divided by delta T. Delta P, the change in momentum, divided by the change in time. Okay, delta P divided by delta T, change in momentum divided by change in time. This is equal to the net force. This is another way to calculate the net force. Okay, so it's not only mass by acceleration, it is also to the change in momentum per unit time. So if the force is constant and acts over a period of time, then from this equation, if you multiply both sides by delta T, you will have the right side F delta T and the left side delta P. So delta P, change in linear momentum, is equal to the product of the average force F by the change in time delta T. This quantity, F delta T, is called impulse. So just like we define momentum as the product of mass by velocity, we define impulse as the product of the average force by the elapsed time. Okay? And the unit for the impulse is very much similar to the unit for momentum, kilogram meter per second in the SI system. We have this very important and fundamental law in physics, which says impulse equals change in momentum. And we ask ourselves, what is change in momentum? Change in momentum means the final momentum minus the initial momentum. And remember, we are talking vector quantities. So this is a subtraction of two vector quantities. That's to say, you may be dealing with components along one direction, or you may be dealing with components along 2 or 3 directions, depending on the problem. So the impulse, which is force by time, the product of force by the elapsed time, impulse is equal to the change in momentum. So if there was no change in momentum, if delta P is 0, then the impulse is 0. This is one way to understand this important formula. Another way to understand it, the only way to change momentum is to apply impulse. You cannot change the momentum without an impulse. Just like what we learned in chapter 5, you cannot change the kinetic energy without work. You remember the work energy theorem? We always will need to do work in order to change the kinetic energy. And here we always will need an impulse in order to change the momentum. And what is impulse? It is you cannot change with the momentum without impulse. You will always need an impulse in order to change the momentum. Okay? I hope you all understand this fundamental law. Quite often, the force will not be constant. The force at one moment of time will start acting, it will reach a maximum value, then it will start going down, and at another point in time, T final, it goes to zero. So how to calculate the impulse? For such situations, the area under the curve is equal to the impulse, because the horizontal axis is the delta T, T final minus T initial, this is delta T, and the horizontal axis is F. So you need to slice this area to tiny slices and then to add the areas until you get the total area. The total area is equal to the impulse. Alternatively, you may take the average, like you define this line as a representative for the average force. In that case, the product of the average force by delta T is equal to the impulse. Okay, so average force multiplied by delta T is equal to the impulse, and the impulse is equal to the change in the momentum, delta P. This is a very important law in physics. So the magnitude of the impulse can be calculated graphically from the area, or can be calculated numerically using this equation.